Hi Zara, sorry for the miscommunication and I don't want you to miss out on learning, so I just want to make this video to kind of guide you through a chemical reactivity paper, just so you can use it as a guide. So this is a 2024 paper. I'm just going to go through like the things that I'd write. I'm not going to write full responses, but I'm going to point out things that when I read these questions and I encounter these questions, what I think is relevant and what I would do in these questions. So question 1 is Ty Point is in the South Island of New Zealand, extracts large amounts of aluminium sourced from an ore called bauxite, which contains mineral aluminium 3 oxide, which is this compound over here. One step of the main extraction process is as follows. So this is the chemical reaction they've given us over here. And the graph below shows the mass of aluminium oxide as it reacts with 0.5 moles of sodium hydroxide. So it shows the mass of aluminium oxide, which is actually a reactant, right? And as a reactant, when the reaction goes on, the reactant is being used over time. So actually what happens is that this concentration decreases because it's being formed into its products, which is why you see that this graph over here is sloping downwards, right? The mass of the aluminium decreases over time and it's not linear. So they have two different sections, section A and section B. And first question is, add a second line of the graph to predict the rate of decline in mass of aluminium 3 oxide if 2 mole per liter sodium hydroxide would use in this reaction instead. Assume both reactions are started with the same mass of ore. So, same mass of ore and 2 moles of sodium hydroxide. So, you're comparing that to 0.5 moles of sodium hydroxide. So the difference here is that you're reacting with a higher concentration of sodium hydroxide, which sodium hydroxide is a reactant as well up here. So if you increase that concentration, you are allowing more particles to react in here, and that provides more substrate and more particles to collide with each other. And so there are going to be more successful collisions per unit of time. So the rate of reaction is going to be faster. But also notice that they specify the same mass of ore. Right? If it's the same mass of ore, then the number of moles of the aluminium 3 oxide stays the same. So the amount of starting reactant is the same, and the amount of finished product is also the same. So you'll start at the same point and then finish at the same point as well, but the rate at which this occurs is much faster, right? And so it slopes downwards like this instead. That sort of thing. And so you can see that it's steeper. The new curve that I've drawn is steeper because the rate of reaction increases from increased concentration. And so with reference to the line you've just drawn, explain the effect that this change in concentration from 0.5 to 0.2 molar would have on the rate of reaction. So in your answer, you should include the mass of aluminium 3 hydroxide, each section of the line, and collision theory. So remember that collision theory just states that a reaction occurs when particles collide with sufficient energy and orientation. And the first bullet point about the mass of aluminium oxide, that is just telling you that the start and the finish of both lines are the same because you start out with the same mass. And then explaining each section of the line, so section A and section B, you'll state that in section A, notice how the gradient of this steepness is something like that, whereas the gradient of the steepness of the other graph is something like this. And so the steepness of the second line is greater than the steepness of the first line, which means that the rate of reaction is faster. But then also comment on the fact that for both of them, as the reaction progresses, if you draw another tangent line over there, that the steepness decreases of that curve. And that's just to illustrate that the reactants are being used up. So in section B, there are fewer reactants, and so therefore a slower rate of reaction. And then in section A, the gradient is steep. And then talk about how the new line is steeper because of increased concentration of reactants. Yeah, and that's relating to collision theory, and then I'm portioning them up. Okay, next is for the 0.5 molar of sodium hydroxide solution, calculate the hydronium ion concentration. So here you would use the relationship that Kw, oh, so sorry. You want to try work backwards from here. You want to try calculate the concentration of H3O plus. What is that equal to? And what have you been given? You've been given the concentration of sodium hydroxide. And sodium hydroxide is a strong base, as you should know, which means it fully dissociates into hydroxide ions. So what you've been given technically is hydroxide ions, but you need to find hydronium ions. So the relationship here that you need to use is the Kw constant, which is equal to the concentration of hydronium ions times the concentration of hydroxide ions. And that equals 1 times 10 to the negative 14 at 25 degrees Celsius. So to solve for hydronium ions, it's just 1 times 10 to the negative 14 divided by the concentration of hydroxide ions. And then next is the pH. pH is going to be calculated using the equation pH is equal to negative log of the concentration of hydronium ions, which is exactly what you calculate in the previous question. So they kind of flow on to each other from there. Okay, and then using the principles of collision and particle theory, so it's just collision theory over here. Explain why using a catalyst would help increase the rate of reaction of producing this product. You should include an energy profile diagram to support your answer. So specifically focusing on a catalyst. So catalysts, they increase the rate of reaction, and their mechanism is by providing an alternate pathway or alternative pathway with a lower activation energy. So bear in mind that they don't lower activation energy of the reaction. They provide an alternative pathway with a lower activation energy. And then you can link this to collision theory, which we just described before. It's just particles need sufficient energy and correct orientation to collide with each other to produce a reaction. So the relevant point here is that the lower activation energy. And then an energy diagram they wanted, so they want you to demonstrate how a catalyst would change the energy profile of a reaction. So originally it might have looked like this, right? This is your reactant and this is your product. And labeling this diagram, recall that this over here is your activation energy, and then this over here is your enthalpy change. And so activation energy is going to decrease. And so with a catalyst, it's going to decrease it like so. So it's going to be, this is the new activation energy with catalyst. This can be energy, and this is time. Okay. Superphosphate fertilizers manufactured in New Zealand using phosphorite rocks and sulfuric acid. The sulfuric acid is often produced on site and includes reaction involving oxygen, sulfur dioxide, and sulfur trioxide, which is represented in the equilibrium constant expression below. So recall that the Kc expression is the concentration of products divided by the concentration of reactants. And then the power of them is equal to the coefficient of each of the reactants and products. So give the equation of this. So the equilibrium always denoted by a two-way arrow, and then the denominator is going to be the reactants, and we've got sulfur dioxide, so SO2, and oxygen. And you've been told in the question that they are in gaseous state, so you should put the gaseous state symbols inside here. And then your reactant is, your product is going to be the sulfur trioxide, and also in a gaseous state. And then sulfur trioxide has is squared, so there's a 2 coefficient in front of there. And then sulfur dioxide is squared as well, so there must be a 2 coefficient in front there as well. And the reaction is set up to allow to reach equilibrium. Calculate the concentration of oxygen at equilibrium if the concentration of sulfur dioxide is 0.17 and sulfur trioxide is 0.5. So this is just using that Kc is equal to a certain value, and that value is equal to 32.7, and that's equal to concentration of sulfur trioxide, which you've been given as 0.5 squared divided by sulfur dioxide, which is the 0.17 squared, and then oxygen, which you don't know. So that's what you're trying to solve. Okay, and then next is going to be, you've been given the 3 concentrations of each of them, and then using a calculation, explain why this reaction is not equilibrium. So here you'd use the Kc expression, and then just substitute these values in. So 0.62 squared divided by 0.53 squared times 0.71, and then does this value equal 32.7? If it doesn't, it is not at equilibrium. If it is, then it is at equilibrium. And what you should calculate here is that isn't at equilibrium. So then you'd want to discuss what should it need to do if it wants to be equilibrium. So technically this answer is 1.93. So 1.93 is much lower than 32.7. So if this expression, right, if your fraction, right, a over b is lower, in order to increase the value of this fraction, either the numerator needs to decrease or the denominator needs to decrease, or both at the same time. In this case, both of these instances occur, and if both of them occur at the same time, it means that the products, concentration of products over reactants, the concentration of products must increase and the concentration of reactants must decrease. That means the Ford's reaction is favored. So, explain what must occur for this equilibrium to be established. The Ford's reaction must be favored, since Kc is equal to concentration of products over concentration of reactants. In order to increase the 1.93, increase it to 32.7. This needs to increase and this needs to decrease. Okay, next one is sulfuric acid can be manufactured using the following reaction. So it's sulfur trioxide with water and it produces sulfuric acid. Using equilibrium principles, identify it, then describe the effect on the position of equilibrium. So this is the effect on the position of the equilibrium. So this is in reference to Le Chatelier's principle. So that describes that the equilibrium is going to shift in the direction that opposes any given change to the system. So let's see over here. We have here that water vapor is added to the reaction mixture. So H2O gas is added to the reaction mixture, which means that in this equation over here, water vapor is actually a reactant here. And if you add more water vapor, then the concentration of the water vapor is going to increase. And so you now have what we call an excess of reactant because of the excess water. And so the equilibrium needs to shift in a certain direction to oppose this increased concentration of water. So it needs to get rid of it. And how do you get rid of excess water? You need to use it up. And how do you use it up? You favor the Ford's reaction because it uses up the water to produce sulfuric acid. And so that is how the equilibrium is going to change. The Ford's reaction is favored to use up, so use that phrase, use up excess H2O gas. And then obviously reference Le Chatelier's principle here. And then next is that sodium hydroxide is being added to the solution. So notice here that sodium hydroxide, you should recall that this is a base. And what you are forming is sulfuric acid. So you have an acid and a base. And if you add acid to the reaction mixture, then it's going to react with, if you add the base to the reaction mixture, it's going to react with the acid. And when you react it with the acid, you get this acid plus base forms a salt. And water is a byproduct potentially. But what the moral of this whole story is that sodium hydroxide is going to react with the sulfuric acid, which forms something else. So it's using up sulfuric acid. So sulfuric acid concentration is actually decreasing in this case. And so what is the equilibrium going to do in order to replace the lost sulfuric acid? So that's the important phrase there. Replace lost sulfuric acid. is that it needs to produce more. And how does it produce more? It favors the Ford's reaction, right? Because it needs to produce it. So the Ford's reaction again is favored, but also notice here that when an acid and a base react, you form water as well. So this is not actually included in the assessment schedule, but it's important to note here that an acid plus a base gives you a salt and water. And if water is produced, then the concentration of water over here increases as well. And what would happen, and as we said before, when you add water to the reaction mixture, the Ford's reaction is favored. So that's just another level of complexity and depth that you can demonstrate there as well. So overall, Ford's is favored, and then again, link it to Le Chatelier's principle. And then talking about this reaction can be performed under high pressure. Explain why this is beneficial to the manufacturing process. So key points here, high pressure, and why this is beneficial. So notice how here the context tells us that you want to manufacture sulfuric acid. So the goal is to get as much sulfuric acid as possible in whatever context this is, right? The product is what we desire. And when you increase pressure, in the environment, then this is equal to either a reduction in the volume or an increase in the solute concentration. So there's more particles in a given space that gives higher pressure. And so when you're in a high pressure environment, or when you increase the pressure, again, the system is going to, or the equilibrium is going to shift in the direction that reduces the pressure again. So these are gaseous compounds, and on the reactant side, you've got 2 gaseous compounds compared to the product side with 1 gaseous compound. And so when the pressure of the system is increased, the equilibrium is going to shift in favor with the one with the least number of molecules to decrease the pressure again, right? To decrease the pressure, and that would be by forming the least number of molecules. And so the product side is going to be favored over the reactant side because it has 1 less molecule that's forming. So that when you go from 2 to 1 molecule, you are reducing the number of molecules in that space, which reduces the pressure of that system. So again, the Ford's reaction is favored. Ford's is favored. And then discuss why this is favorable or beneficial to the manufacturing process. Because when you favor the Ford's reaction, again, this produces more sulfuric acid. And so therefore that is the desired product, and therefore what you actually want. And that's why it's favorable or beneficial. So it's really no different to the other questions before over here. They just give you a lot more space to write it because you have to link it to a context of why it's beneficial to a manufacturing process. And also in general, pressure is, you need to discuss what pressure means, right? It's basically like a concentration. Pressure is the number of moles over a volume, right? So it's basically like concentration. So in order to decrease pressure again, you need to decrease the number of moles. Okay, next is question 3. So a reaction of this is a sulfuric acid ion that's lost 1 of its protons already. And then it reacts with this over here, which is a carbonate ion. Identify the species acting as an acid and the species acting as a base in the above equation and their conjugate pairs. So you just need to notice that the sulfate over here, so those are your pairs, right? And then you need to see what happened from the reactants to the products, right? You can see that the difference between the reactants, HSO4 minus, and the product, SO4 2 minus, is that it's missing an H atom or a proton. So what has happened, and then you look at the other one, this carbonate and this bicarbonate, right? What changed over here? Well, it's gained a proton. So there is a transfer of protons such that the sulfate ion has lost a proton, and if it loses a proton or donates a proton, it is acting as an acid. So the acid here is HSO4 minus, and the one that accepts the proton is going to be the base, which is the carbonate here. And then as a result, you now can form conjugate pairs where the acid must be a conjugate base, and they are basically the same species. That is the SO4 2 minus, and the conjugate acid is going to be the HCO3 minus. The other way you can think about it is if you reverse this reaction and looked at the reverse reaction, which one is acting as the base and which one's acting as the acid, and that's why they are the conjugates. So when you reverse the reaction, they have opposite roles. And then write an equilibrium expression for this. Well, you can do this in your own time. So remember, just it's products over the reactants, the concentration, and then the powers of their coefficients, which in this case is just 1. Okay, and then this reaction was initially performed at 25 degrees Celsius to determine the Kc value. When the reaction temperature was increased to 50 degrees, so notice here that the increased temperature to 50, the Kc value increased. And explain whether the Ford's reaction is exothermic or endothermic. So remember that Kc value is products over reactants. So if you increase the Kc value, right, this means that the numerator has increased or the denominator has decreased, or both, which in this case it's always both because it's in equilibrium, it's going both ways. Or the reaction goes that, like, you know, if one gets used up, then the other one decreases. So if one decreases, the other one must increase. So this means that since more product is being formed and an increased Kc value, this implies that the Ford's reaction is being favored, right? And so then, now that we've established that Ford's reaction is being favored in increased temperature, you need to then talk about is what happens when you increase the temperature of a system. So this again goes back to Le Chatelier's principle. So here, you're increasing the temperature, which increases the energy of the system. Or heat energy, sorry. Put heat energy over here. When you add heat energy to the system, what is the equilibrium going to do? Well, it's going to want to minimize this change, so it's going to want to use up the excess energy. So equilibrium uses up excess energy. And what reaction type, endothermic or exothermic, uses up energy? It's endothermic. Endothermic absorbs energy in order to typically do bond breaking processes. And so it's going to favor the endothermic process to use up the excess energy. And so therefore, endothermic must be favored, and the Ford's reaction is being favored, right? So then pair them up. The Ford's reaction is therefore endothermic. So temperature is also a very challenging one to write about and have like a good solid answer for. So definitely practice this question here. And then next is solutions of 0.1 moles concentration were made of each of the 3 following substances. So this is ammonia, which you should recognize as a weak base. And then nitric acid, which you should recognize as a strong acid. And then ammonium chloride, which you should recognize as a weak acid salt. And then explain the pH of these solutions and include a choice of pH value for each substance in the options below, and then a classification for each of the substances and any equations to explain the pH value. Okay, so we've already classified each one of them. So ammonia, we just said, is a weak base. So if it's a weak base, it means the pH must be greater than 7. But because it's weak, it is not as high as 13 or 14, but it's probably somewhere between 9 and 10. So pH is probably between 9 and 10. And why is that? Because it's a weak base, it only what we call partially dissociates. Partially dissociates in solution. And we denote partial dissociation with a two-way arrow. So ammonia as a base reacting with water in an equilibrium two-way arrow to form the conjugate acid of ammonia, which is ammonium, and hydroxide ions. So the production of hydroxide ions, right, if you produce hydroxide ions, that increases. This has a inverse effect on the concentration of hydronium ions, right, because of that Kw expression, right, that we discussed before. It's a constant, so if one goes up, the other one must go down. And so therefore, since the concentration of hydronium ions decreased, the pH is going to increase because it's equal to negative log of concentration of hydronium ions. Yeah, and that's it. And then next is nitric acid. So nitric acid we classified as a strong acid. And so therefore the pH, because it's an acid, is going to be less than 7. But because it's a strong acid, it's going to do full dissociation. So fully dissociates in solution. And so because it fully dissociates in solution, it produces an equimolar amount of hydronium ions, because acids produce protons, which produce hydronium ions. So the pH is likely to be very, very low, and the only very low options we have are 1 to 2. Okay, so then we have to write our equation. So we have to show nitric acid reacting with water, and because it fully dissociates, it is a one-way arrow, right? And so it produces the nitrate ions and the hydronium ions, right? And because this increases, so the concentration of the nitric acid is equal to the concentration of hydronium ions, and so therefore the hydronium ion concentration markedly increases, which then results in the pH falling down significantly to 1 or 2. Yep. And then next is going to be the weak acid salt, the ammonium chloride. So weak acid salt. And because it's a weak acid in there, acids again, pH is less than 7. But because it's weak, it's a partial dissociation. But it's a salt first. So ammonium chloride by itself first dissolves fully into ammonium ion and the chloride ion in solution. So this is a full dissociation because it's a salt. Any salt that goes into a solution is going to fully dissociate typically. And then ammonium is a weak base, we know. A weak acid, and that's going to further dissociate with water. And because it's weak, it only partially dissociates to form its conjugate, ammonia, and some hydronium ions. And so again, concentration of hydronium ions will therefore increase because you're producing it from the ammonium further dissociating. And so therefore the pH is going to decrease, right? But because it is a weak dissociation or a partial dissociation, so let's just write here, partially dissociates. There is not an equimolar amount of hydronium ions being produced from the ammonium, and so therefore the pH is going to be less than 7, but not as significant as 1 or 2, probably between that 4 to 5 range. And then next is going to be discussing the conductivity of the solutions. So ammonia, so it's the same solutions, and they're all in equal concentration. And conductivity, you need to explain the requirements of a solution to conduct electricity. So the requirements for conducting electricity is free flowing charge, or you can say ions, or you can say electrons, right? So they can conduct charge with free-flowing ions. And then compare the extent of conductivity of each of the substances. So the weakest one, so you want to talk about specifically ion count. So the one with the highest concentration of ions is going to have the best ability to conduct charge in this case. And it usually is related to the strength of dissociation. So a better conductor is typically a substance that dissociates more. Or dissociates to a further extent. So, looking at these three, notice how the ammonia only dissociated one time, as indicated by this equation, and it's a weak dissociation, so only partially dissociated, and it produced some degree of hydroxide ions. Compare that to nitric acid. That was a strong acid, so it fully dissociated, so it produced an equimolar amount of nitrate ions and hydronium ions. So there is a very high concentration of ions in here. And then compare that with a weak acid salt. And notice how this salt initially dissociated fully, so it's a full dissociation here, and then further underwent another level of dissociation over here. So from here you can tell that ammonia is probably the weakest conductor here because it is the only one that had only partial dissociation. The other two had some degree of full dissociation. With nitric acid, it was simply just full dissociation. And then with the weak acid salt, it was full dissociation followed by another weaker dissociation. So that is how you would kind of compare and contrast them. And so ammonia is probably the weakest one here. Whoops. Let's go back to red. Ammonia is probably the weakest conductor. And then you would probably talk about the fact that nitric acid and ammonium chloride, they actually kind of have the kind of a similar level of conductivity because they both fully dissociate once. So nitric acid and ammonium chloride, about the same, because they each have one full dissociation. Right, and again, you want to link this to the concentration of free-flowing ions, talking about which one has the most amount. And so that's probably it for that question. You just want to talk about free-flowing ions and then comparing and contrasting the ability of each one of them to dissociate in solution and conduct charge. And that's it. So I want you to have a go at this paper and yeah, let me know how it goes. And you can send me your answers as well so I can give it a look and perhaps like give you some feedback. But that's all. Thank you.